Chapter 7, Transverse Shear, Maximum Shear in a Rhombus. So we want to determine the maximum shear and its location, this time in a rhombus. With the height of 2h and the base of h over 2. That's our dimensions. So let's see how to approach this problem. If we just consider a small element at the top, so our rhombus is A, B, C, D. So that's A, B, C, and D. So we do know tau maximum. We want to calculate tau maximum in the rhombus, and tau average is VQ over I times T. So if you look at to the base of our element at the top, the yellowish element, that's the base for that. If you write down the relation of B prime over BC, over BC, BB prime over BC is exactly like Y if we consider this height Y over H, which is the height of one of this, for example, the top section, because the total height is 2h and it's a symmetrical shape. That's one goes by 1h for top section and a h for a below section. So that gives us a BB prime is equal to a half of y, half of the height, mhm, and that's all T in the formula. Mhm. So that gives us the thickness of our element, which is this is our small element, our small triangular element for calculation of Q prime. Sorry, Q, which is A prime times Y bar prime. Mhm. So if you develop the equation of Q, first moment of area for our A, B, B prime uh, element, and that's A prime uh, times Y bar prime. A prime is just simply a half of T times Y, mhm, a half of base, which is T times Y. So that's a half of T times Y times, if this is Y, mhm, centroid from the neutral axis locates at, so that's H minus 2/3 of Y. Mm? So this is 2/3 of Y, and this is H minus 2/3 of Y, which is the location of centroid for our element from the neutral axis, or the centroid of entire shape. Mhm. And now if you replace what we ha we have in the original equation, that's tau average equal to here, and if you simplify that, it gives you equation 1, which says tau average is a half of V over I times, in parentheses, YH minus 2/3 of Y squared. And the point is Y is for the entire area. I is for entire area. Mhm. Not only our, not only the top section, or not only our element. So let's see how to calculate I for that. So if you remember from previous example, and also from the moment of inertia calculation in chapter 6, I think part 2, mhm, that says if we have the equation 1 and we just want to know what I for the entire area is. So I is, we do know I for each of these triangle about their centroid is a 36 bh cubed. But we need to know what is the moment of inertia about the neutral axis because that's the center of our shape. That's the neutral axis for the entire area. And that's that in that terms, I moment of inertia is two of them because one at the top, one at the bottom. So this is one, this is two, and they are identical to each other. Bh square over 36 for the centroid plus, do you remember we are traveling from uh, center to any other axis, so that's a positive. So plus AD squared, and RD is just a distance from the centroid of a triangle to the base. That's h over 1/3 of h, so that's AD squared. So let's replace the numeric value on the equation, and if you do the mass, it just gives you I is equal to 2 times b h cubed over 12, and that's b h cubed over 6. Mhm. The entire I for the entire area. Mhm. So far, we calculated an uh, moment of inertia for the entire area, and also we get an equation for tau average based on y and h. So the next step is a likewise previous example. If we know tau average is this equation, mhm, and we already have the area, we already have the moment of inertia, tau maximum is nothing but derivation of tau average over dy when the derivation goes to 0 to get the relation of y based on height. Mhm. And how that goes? That if you do the math, it just gives you a derivation of this part in equation 1, and that's h. Derivation based on y, it's yh is just h, minus 2/3 of y squared is just 4/3 of y. It goes to 0, it just gives me y is equal to 3/4 of h, and we were calculating, if you remember, y from at the very top. So it simply says maximum shear occurs at a 3/4 of h from both ends and a 4h from centroid. Mhm. That's how this statement tells me. Mhm. So that's a 3/4 of h if the entire, if this is h. So y is a 3/4 of h from the top, and 1/3 from the centroid, mhm, for tau maximum. That's the location of uh, tau maximum, and let's plug in to the main equation to get the tau maximum by the value of a tau maximum. So if you do so, if you just plug in y, which is 3/4 of h, plugs that in equation 1, it gives you tau maximum by this equation. Hmm? And if you simplify that, because it's just based on v, I, and h, and if you work around and replace the I from the previous section and simplify the equation, it just gives you tau max is 9/8 V over A. Mhm. And area is 2 because we have two part, the entire area. A half of base, whatever base is, for example, our base is h over 2 times h. And that's how we can calculate the tau maximum in a rhombus, which is 9 over 8 shear force, and that's definitely a vertical shear applies on the rhombus. And that's going to be true for any rhombus with any dimensions. Thank you.